It probably won't make you happy, but it'll make me happy. I'll be anticipating perfection on the real final. I mean, the difficulties are 100% the same difficulty. Or maybe the practice is fraction harder than the real one. Okay, so, excuse me, question? That's the same types of questions. It's like I say on the preamble here, if you are ready for this one and you can work it in 30 minutes, you'll do the same for the real exam. I mean, it's hard to make a more straightforward and vigorous promise than that. So anyway, this is just going through the exam so that you can refer the practice final, so you can refer back to it in case you have any trouble when you are working it out. So I'm assuming everyone here has given it a shot, and you're just here to clarify a few things. That's all good. I have the material also worked out, with the math form. So I don't know which one will be best for us. We've got everything you need. Okay, so please prepare a good cheat sheet, and that means having code and math. And then this is the final will be an individual exercise. You can take it anywhere you want. So it'll start at 10:30. We'll be connecting to Zoom before that. Hopefully you'll get on there. We just like to see everybody on Zoom to know that if you have a problem, you can get access to us and stuff, but you can have your cameras off once you get going. Okay, so we're not trying to do anything. We're not putting anything about lock down your browser. There's nothing like that, okay? So it's just the honor system. I hope that's good. It might come back to bite me someday. So you're not supposed to communicate amongst one another, but you can use the internet just like you would if you were an intern or an engineer. So you have all those tools available to you, just as you would as a practicing engineer. And if that means solutions to the practice final exam at your fingertips, they should be, okay? Okay, so no one has reached out asking for this preload of the packages, so that's not in the final exam. You'll be asked to upload your cheat sheet to the work folder. You might practice that with the practice final, just to upload a blank PDF or a blank Word doc. You probably have yours in a Google Doc, but don't just put the link in there. Download it as a Word doc, just so you can stick it in there, okay? Okay, so I'm gonna go through them, even though probably the people in the room and the huge crowd online don't have too many questions about some of these first problems, but just in case somebody who's catching this earlier can. Okay, so the first problem, using any integration method you wish, determine the moment inertia about the z-axis for the body defined by F and G, and there's a plot. And you're given, you can assume density is 1 and the thickness is 1 unit, so those parameters essentially drop out of the formula. So this was the really cool integral we did in class, okay? And I think a lot of people were amazed when they saw what they derived by simply integrating along the y-axis. So you can solve it using quad GK. I've got the complete solutions up there. You can see how we hide the solutions in the vocarium Jupyter notebook. It just says begin solution, in solution, and what you get is your code here, right? So that's how it works for you guys. Notice that the formula is rho times h, but you don't really need it for the differential moment of inertia. X squared times f minus g plus a third f cubed minus g cubed. And then you can just integrate it using quad gk. So, super hard. We're doing similar things on the final. Any place where you have to enter functions, we're just doing a friendly check to make sure you don't lose points by doing something like making a typo on inputting the function and stuff. Okay, so that's there. And notice if you mess up on the endpoints, you'll also mess up on this test. So it could be that your function is correct and you fail this, but one of your A and B is wrong. So I haven't put that level of a finesse into the friendly check. So if it fails the function, well, a function needs a domain. And if the domain is incorrect, then the function's incorrect, right? That's how it works. So that's how that part works. And then you've never seen the grading cells. I'm putting it on the screen, some of the stuff long enough so that you can look through it. And I've got the code that I use to make this graph. I just hid it inside the grading cell so I can use this, edit it, and create a new exam someday. Questions on problem 1? Yes.
Back in homework 2, we made functions for the Riemann integral for the upper and lower, and then we made the one that calculated both us by adding two.
A trapezoidal rule?
Yeah. Would that one like that be accurate enough, or like more or less accurate than a quad GK function?
It should work. I haven't checked it on this one, but if we grade it wrong and you're pretty sure you got it right, you let us know and we will go in there and double check that. Okay, it should be good enough. What I'm pointing out here is that you don't have to do that code if you don't want to. You can just really do it like you would if you had access to Julia or Python or MATLAB or whatever C++ code that you have and you wanted to call a package, you're welcome to do that. But yeah, you may have to play with the delta t. Let's see, what did I put? So it's down to 10 to the minus 2. So yeah, you can probably do that pretty well with quad Z, but with trap C. Any other questions? Keep it coming, thank you. Okay, and just since I've got it, yeah, the key thing is so on a good cheat sheet, okay, this one is moment of inertia. What could other problems be, okay? So you might fantasize about that and get the formulas handy. And then the key thing on the exam is that, you know, look what we did here. We didn't call the package. We just said, hey, this is your answer. And I stuck in the rho is 1, h is 1. But everything else is u. Okay, so it's pretty up to you to fill it all in. And for some of you, that's really great because you didn't like the amount of starter code. So here there's essentially no starter code. Okay, so this problem 2 is using numerical integration. And yes, once you've solved the problem 2, why not go back and solve problem 1? Just use that code. There's no reason not to. So you're given a scalar valued function that you are reading from a file. And so this is project one, okay, where you had the data for the drone. It's exactly that. And you can use exactly that code, okay? And what I'm trying to encourage, I should say, what I'm trying to encourage is that if you make your cheat sheet and you get the code and the ideas together, this is what's going to be useful to you when you're taking your next courses. Because then when you want to do something, say, oh, I forgot the Julia commands. What? No, you've got them right there, and it's all in a Google Doc, and you'll be going with your homework buddies, and they're going to go like, what the heck just happened to me, okay? So that's what I want to see, is that it's a reflex for you to pull it out. And so just document what you've learned is essentially what we're doing. Okay, so compute the area of the integral of the function, and then you're to compute the area below the x-axis, so the part shaded in pink. So there's a million ways you can solve this one. You can set it up and use the trapezoidal rule. You can set it up and use right-sided Riemann sums, left Riemann sums. I promise that the tolerances on the grading for the numerical integration are set loose enough that it doesn't matter whether you did trap-Z or one of the single-sided rectangular versions of Riemann integration, okay? And for the negative area, I mean, there's a couple of ways you could do it, and if you're using the single-sided Riemann integration, all you got to do is only add it to the area when the function value is negative and ignore it otherwise. So that's one way to do it. There are other ways to do it. So this is integration. And so what I'll put up slow enough so that you can look at the video and then zoom in on your screen, but I've got it set up where I'm calculating it 3 different ways. You don't have to do that, you just need one. But I just wanted to make sure that all of the different ways would work. So the first way is using the trapezoidal rule. The second way is the left Riemann sum, and the third way is the right Riemann sum. And then there's a fourth way where it's not exactly correct, because remember, it takes 2 points to define a single rectangle. And so if you just sum f sequence times dx, you're putting either an extra rectangle in the beginning or an extra rectangle in the end. But who cares, okay? If everything is done right, delta x is so small that if one rectangle is an issue with you, well, I'll be surprised, okay? So you'll get credit too. Now, initially we had the tolerances set tight enough where that one didn't pass, and it's not what I intended. I just never thought about doing it that way. So fortunately, one of the students in the class just did it that way, and I thought, well, 99.9% or maybe even 99% of STEM professionals might just sum the function at the point times dx for all of the function values. It's a perfectly good approximation of the integral, though it does have one extra rectangle. So trap-Z is more accurate, but nobody's saying you have to have the accuracy super high. Just want to make sure you're comfortable doing numerical integration. And so if there's something like this on the final, we'll also set the tolerances such that it should pass with any numerical integration method that you could come up with. Now, I haven't checked it with Simpson's rule, so feel free to check it yourself, but it shouldn't matter. Questions on part A? Are there any more code I should show? Yep, end of the hidden test and stuff. Okay, so this part, you can do it several ways. One way you can define a function, maybe call it f negative, which is the minimum of 0 and this function that you're given. So what that would do is just set 0 here, the function values here, and 0 there. Okay, so you just define a new function. F negative is the minimum of f at that f of x and 0. Perfectly fine way to do it. Another way is you do this integral, and then you integrate the absolute value of the function, and then you can take the difference and get the negative area. So there's many ways to do that. So let me make sure that all of those different ways are highlighted here. So one, f values negative is min dot so that it's broadcast onto f values, and then f values 0, I just put 0 times the function values, okay? And quite frankly, that's the most straightforward way to get the negative of it. But as I showed here in pseudocode, if you were doing the Riemann left and right integrals, it's perfectly fine. This is doing the same thing. It's ignoring the function when it's positive and not adding that to the integral. Okay, so that's a perfectly fine solution. Super simple. And if you wanted to just get the positive value, guess what you would do? If f sequence is greater than 0, I'm going to ignore the negative things. Okay, so it's that's what that problem is about. Okay, so that's the autograder, and then I've got extra plots hidden in there. And the plotting stuff is not part of the solution. It's just me not wanting to throw away the code that made this plot. That's all I'm doing, is storing it in a place where you guys, it won't bother you, and where I'll be able to find it in the future, or whoever teaches this course next time and has access to it. So how are we doing so far? 100%? Yay, okay. So these are limits and derivatives. There could be antiderivatives, but I didn't put any in there. So I think they're a little bit easier just to write down here. So one is the limit at infinity of a polynomial over a polynomial, and of course the highest order wins in this case as x goes to infinity. And since x is going to a positive value, the sign is determined by the coefficients. If x were going to a negative value, and this was x to the minus, x to the fifth, an odd number and stuff, then you'd have to do a little extra thinking, okay? But it's minus infinity because 4 is bigger than 3, and we have 4 over minus 2 is negative. So you just select that. 3.2 is you have an integral, a limit at a point of a function that is sine of x for x less than pi, less than or equal, less than pi, and x minus pi over x for x greater than pi. So you just take the limit as x goes to pi by doing the left and right side limits. And so for the limit to exist, the left and right side limits both must exist and be equal. And that's what we get, because sine of pi is 0, and then x minus pi is 0 divided by pi. So it's not 0 where we've got something problematic here. So we get zeros, and so we get 0 for the overall limit. Okay. This next one, we needed to compute a second derivative. And if you put the function into ChatGPT to check your work while you're going, I hope that's what you do as a real engineer, okay? Or use Wolfram Alpha Pro. Now, I know, it's simple enough that we can do it, but we can always make an innocent mistake, okay? So we want to calc the second derivative. So the first derivative is the product rule. Derivative of x is 1 times e to the x plus x times the derivative of e to the x, which is itself. And then we need to differentiate that again. And I just wrote down the answer because we've got e to the x comes down, and then we need to differentiate this, which is this. And so I just wrote that down, and then there's the answer, 2 e to the x plus x e to the x. So, yeah, it may be nice to have just one sheet of paper to, do these things. It's not cheating, okay? You can have your cheat sheet printed out. I don't care what you bring into the room or have sitting next to you, but hopefully you're someplace where it's quiet and you can think. And then on this one, what's the derivative of 1 over x squared evaluated at x equals 2 is the original problem. And here, I just wrote the 1 over x squared as x2, a coefficient, and we use the power rule, bring the coefficient down, reduce the exponent by 1. Okay, so that gives us minus 2 over x cubed, and then we plug in x equals 2, and then we get 8 for the x cubed, and so it's minus a quarter. And for those problems, there is a friendly check. And it's just exactly like that in the final exam. There's 4 questions similar to this that have a friendly check, okay? So there's nothing in the practice exam that is setting your expectations in a way that will not be met on the final exam. So, and then there's 4 more limit and derivative type problems that are of a slightly higher level. Each problem is worth half a point instead of a quarter point, and there's no friendly check. And it's the same on the final exam. So this one is, do you recognize the limit of e to the x, okay? And this looks strange because there's an n squared and an n squared, but you do a simple change of variables to make that m goes to infinity. Then you have 1 minus 3 over m to the m. And you guys did this with an x in here. And so you know the answer. So it's just e to the minus 3. So 1 plus 1 over m would be e, and 1 plus x over m to the power m would be e to the x, etc. So, single-sided limit, x is going to 0 on the left. On the left of 0, the absolute value of x is minus x. And then the x's cancel, and we're left with minus 1, so the limit is pretty easy to compute. Now, it looks hard because there's an absolute value, but you just got to think, absolute value. Oh, yeah, when x is negative, it's just minus, okay? So it's 4.3. What's the derivative where you need to use the product rule? And so you differentiate the first term. 3x squared plus 1 times the second term, and then you keep the first term and differentiate the second term. And then there's a chain rule, and you evaluate it at a fixed value of x. So e to f of x, you differentiate it, you get to e to the f of x times f of x prime. So there it is, and the prime of x times sine of x is essentially one that we did earlier. So you get derivative of x, you get sine of x, and then you get x times the derivative sine is cosine x. And the math works out because this vanishes, this is finite. There's no problem with the evaluation. You just get 0. Any mistakes so far? Similar answers to what you got? Yeah? Yes. No, we've had enough people work on it that they let us know if there's a problem. Okay, so now we get to problem 5. Let me go back here. So anyway, you get the friendly check, just like you've seen in several of the projects and homeworks where multiple choice. Hey, I got 3 out of 4 right. I don't know which one is wrong, but I'll figure it out really quick. And then you've got these 4 that we just worked. And bingo. So that's how those go. Gradient descent. Now we're on project 2. We did project 1, now we're doing project 2. Now there's no project 3 on the final in the sense that we are not doing feedback control on the final exam. That's your project 3. You haven't had time to get it, to get a grade back, to digest it. So project 3 is verboten for the final exam. It stops at kind of the first half of chapter 10, where we use Laplace transforms to solve differential equations. So that's the end of the material for the final. Okay, so you're given a cost function. How do you know it's a cost function? Because it's called cost. Okay, now I should have called this constraint 1 and constraint 2, but I didn't because that would seem kind of long and awkward, but it's g1 of x, g2 of x equals 0. So gradient descent, compute a local solution. So run me, I define the cost and constraint functions as well as the point x0. Yeah, so in this problem, you have enough stuff to do that I didn't want you messing up the copying of the functions and stuff. So, and it'll be, if there's a gradient descent or a Newton-Raphson type thing, there'll be something similar on the final. Okay, so it's focusing on, okay. And then the sanity check is when you're running and using, you could calculate your gradients by hand and program them up, or you could use forward diff. However you want to do it, you can check them at the initial point because it's given to you here. So that's just a sanity check. And then the friendly check is you're given a bound on what the cost is at the correct solution. So, the chances of you getting something and it's wrong and it lands in there, it's pretty small. I mean, it's not 0 probability, but it's pretty small is the idea, okay? So, and I think this is more clear. So we're going to program this up. X star is argmin, G1, G2. We're given the initial point. So, because these problems, we're not calculating a global solution. There could be many local minima, and so where you start is important. So I don't want everybody starting at some random point, so I'm giving you the initial point. Okay, so we want to find xk, a descent direction that satisfies the gradient of the cost function. Here, the cost function is f, dot product with the descent direction is negative, and it leaves the constraints unchanged to first order. So there's many ways to do this. You can apply Gram-Schmidt. Here's one of the ways we've seen it. You've got a third way from project 2. You're welcome to use that code at the very end of project 2. It works, part 2 of project 2, it works great as well. Let's call delta x our descent direction. We'll make sure we know we're descending, so we'll put minus the gradient first. And then we're going to add components of the gradients of the two constraints, and we're going to choose the alphas such that delta x dot with these guys becomes 0. And the easy way to solve it is just to write this as the columns of a matrix. So the gradients are the columns, put them in the columns of a matrix that I'm calling very cleverly G. And I take my coefficients and I just stack them up. So alpha 1 grad G1 plus alpha 2 grad G2 is the same thing as alpha 1 times this column plus alpha 2 times that column. And then if we want that delta x dot, the gradient of the cost is 0, well, if I have two vectors and I do their dot product, I transpose one and I multiply them. Okay, so I transpose G and I multiply it times G delta x. That's doing the gradient. That's doing this calculation for I equals 1 and 2. And so you get this nice little formula, G transpose G times alpha equals minus G transpose grad F. And if you use backslash or inverse, no one's going to look, okay? So, of course, you should always use backslash to solve this linear equation, because in real life you're going to have 30 or 40 constraints, etc. But on the final exam, you're not going to have 30 or 40 if you get one of these types of problems. So you just solve for alpha, and then once you plug in alpha, you have your delta x. And so the way gradient descent works is I give you an x0. It doesn't satisfy G equality equals 0, so you should use NL solve to get a good initial start. Try to set up loops that don't diverge to infinity by running forever. So it's perfectly fine to make this a for loop for k equals 1 to k max, and then just put a test. If the step size gets sufficiently small, you just return the solution. But, in theory, a while loop is fine as long as you exit the while loop if you exceed some maximum number of iterations. And so this is just an and here. And so you would update xk with s times delta x, and s is a positive number. In the problem statement here, you're given a suggestion for s. Seems smart to use the suggested value, but you're welcome to use something else. As you're updating X, if the constraints are no longer sufficiently satisfied, you want to run NL-solve again and update it. And then it doesn't do any good to have K less than K max unless you increment your K in the loop, okay? So please do that. And then you'll get your X star and you can calculate F star. Let's see if that's what we do here. So I double checked my solution with jump. I would not recommend you take the time to do that, okay? Unless you are really a big fan of jump, okay? It's much quicker to do your own bespoke loop. So I calculate the gradients, and you don't need to put the nobla sign. You can just say grad F, grad G1, grad G2. And it's forward diff dot gradient of cost, okay, and gradient of G1, gradient of G2. And then I wrote a function to compute a descent direction, but you don't have to have it as a separate function. You can just embed it. So let me just go through this slow enough that people can, online watching the video, see what I'm doing. So back to the top. If you're using NL-solve or forward diff, linear algebra, you've got to call those yourself. We're not giving you anything in this problem. So I wrote a function to do the descent direction. And then this selection equals 1, ignore it. That's just the one that's doing the gradient descent that we just talked about. So it sets things up with a tolerance. You know, that's pretty tight. K max is 1,000. 10,000 is fine, okay? 10,000 is perfectly fine. You will not need 100,000 iterations, okay? Using the suggested step size. What happened? Where'd it go? Using the suggested step size. G equality is just the two functions, one stacked on the other, so that NL-solve, it works on a vector of functions. And then you can get the result. The xk is the 0 from NL-solve. And then I use my descent direction from the current value of xk. If your descent direction goes to 0, you have converged. So I'm just defining that as an error. And so my while loop is k less than k max and error greater than whatever tolerance I gave. And then it's pretty much what we had before. Organized slightly differently here, but you could have organized it just as I did the pseudocode on the thing. So yeah, this is pretty good pseudocode. Questions on the gradient descent? Yeah, please.
In lecture, we defined alpha as, I forgot what it was the dot product of the gradient of the cost function and the gradient of the equality constraint.
So that works for when there's one constraint? Because I was only subtracting off grad of G from the thing. So if there's 2 or 3 or 4, yeah, just line them all up. So let me repeat the question. So in lecture on the gradient descent, we went through in a lot of detail when there was a single constraint. This problem has 2. And with a single constraint, we wrote delta x is minus grad of f plus alpha, and there was no second term. And so then there's a simpler formula for alpha. Here, you can do the grad g1 dot x and set that equal to 0, and you can solve for alpha 1, and you can do grad G2 and solve for alpha 2. This is just a way to use linear algebra and do it all at once. Okay? Because this condition means the gradients of the constraints transpose times delta x for you guys, okay? It goes this way, is zero. That's why this is transposed, because these columns, when I do dot products, they're transposed, they become rows, and I multiply them by the other column vector, and I get a 1 by 1. Okay, so that's what's going on there. And so this formulation, if I have 17 columns and I have 17 alphas, and this doesn't change, okay, so that's what's good about it. On the final, you will not have 17 constraints if there's a gradient descent, and you will not have 17 functions to find a root of if there's a Newton-Raphson, etc. Okay, so it'll be things where you know what you're doing, the calculation's quick, you're in, you're out, you've got a solution, you move on. Does that answer your question clearly enough, or is there some more details you'd like to do?
I think we can move on.
You think you can live with that? Yeah, so post on Piazza, and then Max can write that out and compare the two solutions and just do that, okay? Be good review, Max.
Yeah.
Hey, you know, I don't memorize any of this stuff, okay? So I just kind of know that this means I'm descending, and this means I'm not changing the constraint. And then I just write down the linear algebra, and then I get the equation. I don't memorize any of that stuff, okay? It just, Now, I know there's a lot of people who could memorize all of that with no problem whatsoever for life, but I'm not one of them. Okay, problem 6, numerically solve an ODE. So the first part, I'm teaching you Euler's method. We discussed it extremely briefly, but I wanted you to do it, so I figured if it's on the practice final, you'll do it. And then the second part is just using the differential equations package. So, makes sense. Now you know that method's there, you'll have your code for it. And so remember what Catherine Goebel was doing was calculating the trajectory of John Glenn's spacecraft as it went from an elliptical orbit and then had to transition to a parabolic path to land in the ocean. And so it enters the atmosphere super high, so there's very little drag when there's very little air. So I put a differential equation that models that. Okay. Okay, and if this is the acceleration, then you've got to integrate once to get velocity and integrate again to get position. So there's the differential equation. So the ODE is x dot equals f of x, where dz dt is the velocity and dv dt is the acceleration. Okay, so anything that requires a differential equation, it's got constants, I will give that to you. Okay, so we're not going to lose points because we didn't copy all of this stuff down. Okay, so, and well, I was very kind and I even included the using differential equations because it seemed the most natural place to put it. So this is the differential equation as a function orbital ODE. So dx is what's being returned, which is x dot. Remember, a d, just like in the Lagrangian models, for dq is q dot. So that's what I've done here. Initial conditions on the position and velocity, semi-realistic. And then you're given Euler's formula, and if you remember when we did it in class, we just said x dot equals f of x, and we said x dot is x of t plus delta t minus x of t over delta t. And then we solved for x of t plus delta t. So that's how you get Euler's. Okay, instead of delta t, it's using h, which is a common step parameter for these types of methods. Okay. And here there's more starter code than the others. And it's simply because you could take your values and do them like here, where you go x at time 1 is in the first column and x at time 2 is in the second column. Or you could have stacked them quite fine and put x at time 1 is the first row and x at time 2 is the second row. And I just wanted to remove all the ambiguity and just set up the matrix. Okay. So you have to put Euler's method in here. And since Euler's method is one line, and then this is very particular here. I mean, we're going to follow that differential equation until we splash into the ocean. So we got to stop someplace. And so we say the ocean is at 0 altitude. And so as soon as we get a value that's less than or equal to 0, we just break the integration. And I did that for you. Okay, so that's the same starter code you had. And then you got to put in Euler's with a for loop. It's up to you how you want to organize that. But you get x dot by just plugging in, calling the differential equation. Doesn't matter what you apply for dx because it doesn't depend on that. It depends on x, the parameters, and time. And then you do x plus the current value of x, and then dx times x dot times delta t. And then that goes into the next x mat. So you read the previous x, and then you calculate the next x and just stick it into x mat. And then that's the code that was already given. And then so that, especially since you've never programmed up Euler's method before, you're given an idea of what the splashdown should be. And then the second part, you solve the same differential equations using the differential equations package. And we don't do anything for you except, well, we've already defined the differential equation. It was called orbital ODE. And we set T-span, because you guys haven't used this package 45 times. You've only used it once or twice, and mostly in project 3. So I set that up for you. But the rest of it, you need to set up the ODE problem, call the solver. It won't matter which solver you use on the equations I give you. They'll all give you the same answer, but this is the basic one, TSIT 5. It's a Runge-Kutta. It's it's a Simpson's rule with roughly fifth order polynomials, okay? So it's a pretty good solver. And then this is just making plots, so it's nothing for you guys to do there. So Euler, you got to set up the time vector. This stuff was done for you. The time vector, you're given dt and t max, and length of the time vector. Create a matrix to store the states of the differential equation. It's 2 for this problem, because x0 has 2 components. Put the x0 in the first column, and then a very simple for loop where you read out the previous one, that's it. Take the ODE at that point times dt, add it, and then you shove that into the next value of x, and then you just iterate. And then using differential equations, you need to use the ODE problem command and the solve command, and we tell you to call the answer my ODE solution. We don't tell you to use tsit5, but if you have one of those problems, it's a perfectly good solver. But if you've got another favorite one, and your answer differs by ours by 10 to the minus 4, and we are at 10 to the minus 5 on the tolerance, which is ridiculous, but who knows? We'll fix it if you let us know. Question on solving ODEs?
Will we need to do one by hand?
I hope you don't solve too many ODEs by hand as a professional. And when you solve an ODE by hand in a course, it's going to be separation of variables if it's nonlinear, or it's going to be Laplace transforms. And we're doing it by Laplace transform in the last problem, okay? That's just how ODEs are solved these days. It could be that I am under-preparing you for your next classes, but I don't think so. I've taught some of those classes, not all of them, of course. And I've done this for 40-something years. Yeah. The number of nonlinear differential equations that have closed-form solutions, we kind of went through them once in class. There was like 7 examples, okay? Yeah. Not worth memorizing. I just went to ChatGPT, give me a list of all the examples, okay? So the last problem, Laplace transforms applied to ODEs. And so the first problem is to compute the transfer function by inspection. So we have it set up. I had SymPy and everything, as I'll show you in a second, defining the Laplace variable s as a symbolic variable. And you guys know this defines the numerator. And whether you put the s first or the 4 first, it's not going to change the answer. S plus 4 and 4 plus s are the same. And remember, with transfer functions, the initial conditions are all 0. So this is s cubed, this is 6s squared, this is 11s, and this is 6. That's the transfer function by inspection. Next part, use SymPy to solve the equation here when the initial conditions are all 0, and the input is e to the minus 5t us of t. So you may wish to have on your cheat sheet the table of Laplace transforms, or you're going to have to use the SymPy tools to compute the Laplace transform of the input signal. I promise you, on the final, the signal you need is on that cheat sheet, okay? It's not something weird where you've got to do 25 contortions to fit through the little tiny slot I allowed to create a solution. No, it'll be this. And if this were +5, this would be S minus 5. The signs are always opposite. It's unfortunate, but that's how the math works out. It's not me, okay? And it's not Max, and it's not Mia. We did not set that, okay? It comes out of the definition of the Laplace transform. Okay, so if all the initial conditions are 0, then the Laplace transform of y is the transfer function times the Laplace transform of the input. And you are told to use the function SymPy.inverse Laplace transform. And so that's all it is. Okay, so here it is in code. Okay, you've got differential equation that I just showed you, where y is the system response and u is a single-sided control input. Part A, compute a transfer function. Part B, use SymPy to determine the time domain solution when all initial conditions are 0 and the input is e to the minus 5t times a unit step. If you have a problem like this, this script will be there, but I'd recommend having them in your cheat sheets so that you have them when you're doing it in, I don't know, Rob 320. I don't know if they need differential equation solved there, but who knows? Or Rob 311, but you've got the calling sequence. But I don't want people wasting time because they didn't include time when they defined the symbolic variables. I don't want people losing time because they forgot to put SymPy in front of symbolics and stuff like that. Okay, so I'm just trying to make it as straightforward as possible to demonstrate that you've learned how to solve a lot of problems very quickly and accurately. So the first part, once again, is the transfer function. So that's the solution is that hard. You just write it down. It's one line, okay? And then we check them for you. Okay, we run it through a series of tests because, if there was a minus sign here and you missed it, I would feel horrible that you lost all the points because of a minus sign, okay? So we just check it, and then you'll go back and you'll find it very quickly if there's a minus sign or something, okay? Or if you put 4s plus 1 over here just by accident, you'll find it very quickly. So we just run a quick check. Okay. And then determine the time domain solution with SymPy, and we give you the command you're supposed to use. All the initial conditions are 0, and so literally, you need to define the Laplace transform of the input. Then the Laplace transform of the output is the transfer function times the Laplace transform of the input. And then you call the command with the Laplace transform of y, and then I guess you could have a different independent variable, doesn't have to be time. You could be using something else besides s, I guess. So that's why they're there. And then we do some friendly checks on that as well. So Oh no, there's no friendly check on that part. Just the auto grader. So we friendly checked the transfer function, and then this last point there, you're naked, you're all on your own, frightening. And then the end, bullseye. Comments, thoughts, questions? Kind of know how to organize your cheat sheet? I would have solutions to problems like these, and then friendly amendments, okay? What's a friendly amendment? Well, if this is moment of inertia, and you've already got that on your cheat sheet, what other mechanical thing did we do? Okay, you might put that on there. So, could be total mass, could be center of mass, you know, those types of things. And the differential equation, believe me, if it has non-zero initial conditions, it's going to be low order, so you don't have to do a ton of Laplace transform stuff and writing it down in code. So, but you know, could be solve y double dot plus y equals something simple with y at 0 equals 1 and y dot at 0 equals 2, you know. Those would be easy amendments, and you could solve that with just a small, simple change to the y of s, etc. How are we feeling? You don't like timed exams, I know. But my guess is you're going to have at least 15 minutes that you don't know what to do with. Devin, comments, questions? Kane, anything? I see you're on there now.
I don't like timed exams either. I don't think you guys are in for many surprises here, which is good.
Yeah. Yeah. And you know, it could happen that vocarium goes down. If that happens, we just remove the final exam from the grades and just do it with the other, okay? And if somebody was needing the final exam to get that extra little bit, that's what we'll do, okay? So we'll always give if there's a technical glitch, it'll always be resolved in favor of the student. We won't reschedule it for later in the day, okay? That's not going to happen. So far, I think nobody has told us where they're taking the exam. Have you? You going to come here? Yes. Okay, I'll be here.
Or I can be here and online too.
Yeah, so Max, Kaylee, and I will be in the room and online. I don't know, Mia, if you want to have somebody, maybe you can look through the final exam and be there, but I don't think there'll be that many questions because of the problems are so patterned on this. I think you guys are just going to sit down and work your way through it, and there's going to be no questions. And there's not going to be a typo, I promise. Yes.
I recall during project one, I and a few other people accidentally wrote code that made vocarium unable to run. And I remember you said afterwards there was like a way to fix that. So how exactly do you fix that in case that occurs?
Yeah, so if your kernel is disconnected, watch this video, okay? But here's a live demonstration. So now, because I haven't run anything in a while, let me get the kernel running again. And then, oh, let's suppose that's running forever. So we go here and we hit end lab. Yes, I do want to end the lab. And then you don't need to do anything over here on kernel. You just go to the cell you want to run, and then the kernel will reinitialize. Now, when you hit end lab, if it's in a deep it's your function, and then it's another function in Julia, which is calling another function in Julia, which is calling, it could take a while for it to pop back out, up to 30 seconds or so, which will seem like 4 days when it's you in the exam, okay? That's exactly how it would feel. But yeah, so you just hit in lab, yes, and then go to any of the, doesn't have to be the first one, just go to it, and it will reconnect to the kernel. If it doesn't do it the first time, just hit the thing again, and you'll see kernel is initializing at the bottom. And then status running 1 of 1 cells. I would not recommend to hit run all, because who knows what's going to happen. So just go through them one by one. Is that clear enough?
That's the solution when it says kernel disconnected?
No, it's when, suppose you created a loop on gradient descent. So the question was, is that the solution when the kernel is disconnected? No. Let's suppose I'm doing gradient descent and I didn't do k equals k plus 1. And I'm not descending, I'm ascending, and so my delta x is never going to 0 or something, and so it just runs forever. You're going like, holy smokes, I bet Professor Grizzle didn't want this to run for like a day and a half, okay? So your thing is running, so you got a spinning wheel here. You come down here and you say, end lab. Yes. Let it stop spinning. Fix your error, look for it. So if we're on the gradient descent, oops. Or you did a divide by 0 or something. Whoa. Yeah, it's really nice if you actually include the k equals k plus 1 line, okay? Because, yeah, I'm going to stop if k reaches the max, but I never incremented k, or I forgot to put this in my while loop or something like that. And that's when you come down here and you go end lab. Bingo. And then you'll start again. Then this, go to work, select, upload, and I don't know, wherever you keep all your junk, and just upload something. Robust fall prediction, well, that's a huge file, so I won't do it, but you just upload it and hit open and it's done. And then your thing will be stored in there. And if you get a really bad grade on the final, we're going to look at it and say, wow, that's the shortest cheat sheet I've ever seen. And go, huh, didn't really take us seriously when we said, if you can do the practice final in 30 minutes, you'll finish the other one in plenty of time. So it's literally we're shaming you into creating a cheat sheet, okay? That's horrible to say that, okay? But literally that's what we're doing. Any other questions? Okay. I expect median is going to be like 90%. And this is not to put pressure on you, it's to take pressure off. It's just, there's nothing contorted on the exam. If you can wrap your brain around the practice final, you're going to wrap your brain around the other exam and feel like you're well prepared. And you're going to have a cheat sheet that will allow you to do well in your follow-on courses. Okay, so that's it. Thank you guys for allowing Rob 201 to exist this term. I'm deeply grateful. The college is looking at the first-year math courses, and it's not been voted upon by the faculty, so there's a lot of steps to go. But the college is negotiating with math to have a first semester year one linear algebra course that looks so close to Rob 101 that I'm going like, oh, that's Rob 100.99. Okay, got it. And then there's a second semester freshman or first semester sophomore calculus that combines math 115 and math 116, not 216. So we'll still be offering Rob 101 and Rob 201 for the robotics students. And I don't know if other departments will be so brave as to let their students take this. But we're getting the other departments to say, if you've had 201, you're ready if it requires 115, 116, or 216. And if the only reason you have math 115 is because you need gradients and Jacobians, we've got that covered as well. But we didn't do any multivariable integration, so there's nothing like that. So yeah, so this robotics is leading the way. But without brave people who are willing to take these pilot courses, okay, it doesn't happen. So great, I'm grateful, and the department is grateful that you guys did that. And Max and Kaylee, thank you for all your participation in setting stuff up. Mia, since you're here, I'll thank you, but there's a small army of us who tried to make this course ready for the 100 students that didn't come.
Yeah, we were so ready for that.
Oh.
Giant lunch for everybody.
We were so ready for that, but maybe winter 27 out of 6, I don't know.
Gives you a little more runway.
Yeah. And if the final isn't too bad, you guys will put good words on the street and things will happen.